our last speaker is probably one of the few who might have been to all string pheno conferences thus far, Alon Faraggi. He'll talk about beyond the standard model phenomenology and modular maps.
Right, thank you. I'm just trying to unmute myself. I'm not used to using the Zoom on my laptop. Right, so on Windows. So thank you very much, Brent, and thanks all. I'd like to thank the organizers, Jim and Fabian, especially on behalf of all the speakers. I mean, being the last one, so I think it's been a fabulous experience. Unfortunately, not on site, but there will be in 2025 another opportunity to hopefully to do it in Northeastern. And I hope that my battery is not running out. Right. So what I will talk about today is about what I call modular maps, and if anybody has a different, more appropriate name, then please tell me. And BSM phenomenology. So what do I call modular maps? What I call by modular maps is just any mapping by a group of 4 worldsheet periodic fermions. So one well-known example is the example of space-time supersymmetry. And I will discuss spin-vector duality, recent work done with Stefan Gut-Nibling and my student in Liverpool, Martin Hurtado Heredia, on realizing spin-vector duality in the effective field theory limit of string compactification. I will use spin-vector duality to discuss how we construct a string-derived Z-pi model and related collider, or I will discuss a little bit sort of work that we're looking into in terms of collider phenomenology with Marco Guzzi, and then the final example of such a modular map is non-SUSY string phenomenology from 10D tachyonic vacua that I've been pursued with my students in Liverpool, Ben Percival and Victor Matthias, over the past year. So the first, no, I'm not in full screen mode, I guess. So the first question to ask is why? Why should we do this kind of work? It's a question that I ask myself, whether it continues to be relevant or not. The data tells us that the standard model, I sometimes call it the standard parameterization, is the correct description of physics as accessible energy range. Since 2012, we have seen a resonance that appears to be to comply with the Higgs resonance. It seems that electroic symmetry breaking is perturbative with the Higgs at 125 GeV. And the standard model strongly hints toward the realization of unification structures in nature. The evidence is from the multiplet structure, Lagrangian gunning of the parameters, proton stability, neutrino masses, and so forth. So there's strong evidence. Now, suppose we see some beyond the standard model physics at, say, the LHC. So, and we do quantum field theories. What are we going to do? We're going to add parameters. And then fit the data. Nothing constrains us. So if you do just quantum field theory, nothing constrains you. You can add as many parameters as you want to fit the data. The only meaningful way, to my mind, that does actually constrain you is synthesizing the standard model with gravity. And string theory allows us to do that. So string theory constrains, doesn't allow us to add as many parameters as we want. So that's, to me, is meaningful. In fact, the only meaningful thing to do with the present data. Now, so when will this stop being sort of relevant to my mind? I think the basic question is, at this point, is the Higgs fundamental or composite? Is it a star model Higgs? Is it a multi-Higgs system? And the SSC type machine might be sufficient to address these questions. If the Higgs is composite, for example, I will do something different. I mean, I will not continue to pursue this. Now, since the late 80s, we had the fermionic Z2 goes to orbifold that sort of allow us to look at the phenomenology of the star model and unification. And for example, it produced the first minimal supersymmetric standard model from string theory and so forth. Since 2003, we've been working on classification of large number of these vacua, and recently Ben Percival and Victor Matias have sort of pushed this further by adding tachyonic TD vacua into this program. So the idea is that this fermionic Z2 goes to orbifold, they indicate the structure of the Z2 orbifold as maybe having some relevance for the observational data. So the idea is to try to probe it from the different limits of the yet sort of mysterious fundamental theory that underlies the string theory in 10 dimensions. And in addition to these supersymmetric theories, we also have the non-supersymmetric theories, and in particular, we have also the tachyonic non-supersymmetric theories in 10 dimensions, and we can compactify. So we have the SO16 cross 16 that is non-tachyonic in 10 dimensions, and we can compactify those and build models in 4 dimensions that are tachyon-free. So the idea is to try to incorporate them into these phenomenological explorations, and some people have sort of pursued this over the past few years. So let me just give you just a few relevant points about the phenomenological construction. So in the light cone gauge, in the left moving, all the degrees of freedom are represented in terms of fermions propagating on the string world sheet. In the left moving sector, we have the 8 Ramon-Neveu-Schwarz fermions, then we have 12 fermions that correspond to the compactified internal dimensions, and then we have in the right moving sector 12 fermions corresponding to the compactified dimensions. And we have 16 complex fermions, 5 of which produce our GATT-SO10 symmetry, and 3 produce U1 symmetries, and 8 produce the Eden SO16 gauge symmetry. So we calculate the vacuum to vacuum amplitude. The fermions, when you parallel transport them around the non-contactable loops, pick up a phase, and this phase is, say, if the phase is here is 0, this will correspond to a Neveu-Schwarz fermion, or antiperiodic fermion on the worldsheet, and if alpha is equal to 1, this will be a Ramond or periodic fermion. We span the partition function by summing over all possible spin structure assignments, and we have in this sum this one loop GSO phases. Models are constructed by demanding that this partition function is invariant under model transformation. And we construct models by specifying a set of basis vectors and the one loop phases. So this gives me to my first example of a modular map. So this is a set that we use to classify models either with SO10 symmetry. So you have this set of basis vector preserve n equal 4 space-time supersymmetry. This set here correspond to internal shifts in the internal dimensions. These are the 2 Z2 cos the 2 orbifolds, and sectors that break the SO10 symmetry to one of its subgroups. And this sector here is the generator of space-time supersymmetry. It has exactly 4 complex periodic fermions. So it's and whenever you add it to any other sector in the model, it produces the space-time superpartner. So this is an example of what I call a modular map that we are all familiar with. So then we enumerate the space of vacua by varying the one-loop GGSO phases. And so, for example, in this case, which are Petit-Salam models, we have 66 independent phases, so corresponding to 2 to the 66 distinct vacua. And over the past year, we've been collaborating with computer scientists at Liverpool who like these programs that are called satisfiability modular theories. And in particular, Ben Percival has implemented the usage, the utilization in our classification program. And they can lead, so this is a very useful tool, they can lead to more efficient running time by 3 orders of magnitude, which is particularly important when you want to classify tachyonic vacua and you want to analyze all the tachyon producing sectors and eliminate them. Then that can be very, very computer-wise time consuming. So let me talk now about the spin-vector duality. So we observe this in classification of fermionic vacua. There is a duality under exchange of the total number of spinors and antispinors and the total number of vectors. And this is a density plot of the number of vector models versus, say, the total number of vectors and the total number of spinor plus antispinor. And you see it's symmetric under exchange of rows and columns. It's easy to understand why there is such a symmetry when you extend the symmetry to E6, because there the representations are 16 plus 10 plus 1, which make up the 27, and the 27 bar is 16 bar plus 10 plus 1. So if you count the total number of 16 plus 16 bar, it's equal to the number of vectorials by virtue of the enhanced E6 symmetry. Now, the statement is that when you break the E6 symmetry to SO10 cross E1, there are 2 dual vacua that are in which the total number of spinor plus antispinor, total number of vectors are interchanged. We can sort of demonstrate this duality by considering an orbifold. Z2 goes to 2 orbifold, where 1 orbifold is a freely acting Wilson line, which breaks the E8 cross E8 to SO16 cross S16. And the second one is just a Z2 twist of the internal coordinates. So here we have a single Z2 twist, which breaks n equal 4 to n equal 2, and the E7 rather than E6 is broken to SO12 cross SU2. So the spin-vector duality will be in terms of representation of SO12. We can analyze partition functions, so we have this is a partition function. It will have 2 modular orbits. There is a discrete torsion between the 2 modular orbits, and so there is a spectrum which attaches to the massless modes of the untwisted lattice, and there is a spectrum which is attached to the shifted lattice. So this will be massive, and this will be massless. And we have two possibilities. We have a discrete torsion here, so there are two possibilities, plus minus 1. So analyzing this partition function, we see that for one case, one choice of the discrete torsion, the 0 modes attach themselves, the 0 mode of the internal lattice attaches them to the vectors, and the spinor attach themselves to the massive modes. Whereas for the opposite, this choice of the discrete torsion, exactly the opposite happens. So this is a realization of this spin-vector duality in terms of this discrete torsion. So now with Stefan Gut-Nibling and my student Martin Hurtado-Heredia, what we did was we studied this spin-vector duality on resolved orbifolds, so essentially in the effective field theory limit of these worldsheet constructions. And we demonstrated that there is such, indeed, such a spin-off vector duality operating in this, in the effective field theory limit. So in a sense, we are going here from the land, maybe from the worldsheet ultraviolet complete series to the swamp. So this gives us a tool to look into the modular spaces of 2,0 computifications in the effective field theory limit. Waffer and Witten in 1994, they discussed the role of the discrete torsion in Z2 cos Z2 orbifold in mirror symmetry. So they demonstrated mirror symmetry in terms of the discrete torsion in between the two twists of the Z2 cos Z2 orbifold. What we're doing here is something similar. I mean, we are looking into the role of the discrete torsion here, not between the two twists of the internal space, but between a twist of the internal space and a freely acting Wilson line. And what we're looking into the imprint of the worldsheet modular properties into the effective in the effective field theory limit. So what this has to do with modular maps that I sort of am looking for? So we can change the basis, the fifth fermion basis to this basis. So this basis breaks the 16, the rank 16 gauge group to factor the untwisted rank 16 gauge group to SO8 to the 4, and then the twist will break one of those to SO4 cos SO4, and then to SO12 gut symmetry will be obtained by from enhancement. So the SO8 cos SO4 will be enhanced from twisted sectors to SO12. So the SO12 enhancement here is obtained by adding, just like we do with the S vector that I discussed before, by adding so to a given sector, adding Z3 for some choices of the discrete torsion will enhance the gauge symmetry to SO12. And the spin-off vector map is induced by this Z4 basis vector. So this Z4 basis vector, which is the right-moving spectral flow operator, it is exactly has the same structure as the S vector. The S vector changes between space-time fermions and boson, whereas the Z4 changes between spinor and vectors of the SO12 enhanced symmetry. So it is the right-moving spectral flow operator, and it is precisely this kind of modular map that induces this transformation. And I should add that the picture, this spin-off vector duality picture, extends to computification with interacting internal CFTs or to minimal models. This was demonstrated in a paper with Panos Athanasopoulos and Doron Gepner some years ago. So what is the BSM phenomenology? So if we start with E6 and we break E6 to the standard model cross, we have two extra U1s in beyond the standard model in E6. One of those typically will be anomalous, and the other one we have to break at a high scale to induce the seesaw mechanism. So it's very difficult to build string models that allow the Z prime to remain unbroken down to low scale. Indeed, for many years, we and others, I mean, with my students in Liverpool and for example, Pati, looked for U1 symmetries that do not have an embedding in E6. But then we showed with Viraf Mehta that, in fact, if you require the correct values of sin squared theta Weinberg and alpha strong at the electroweak scale, then this demands that the U1 Z prime is embedded in E6. Together with John Rizos, we constructed such a model, and the way we did it, we fished out a model which is self-dual under the spin-off vector duality. So effectively, the multiplets reside in complete E6 multiplets, but there's no enhancement to E6. So that's how we kept this U1 unbroken, could remain unbroken down to low scales. And that gives very interesting phenomenology because there will be additional states, so keeping it anomaly free down to low scales, say 5 TeV, mandates that there are additional states that will get their mass at the Z prime breaking scale. So they can produce phenomenology which is very relevant for the LHC and say the existence of stellar neutrinos. Why would stellar neutrinos not get a mass at the string scale? And if this Z prime remains broken down to the, say, some intermediate scale, this can explain, these stellar neutrinos are chiral under this U1, so this can explain how they can stay unbroken down to low scale. These states here get a mass of the order of the Z prime, but there is a multiplicity of them. There is a generation multiplicity, so they can be relatively heavy, so outside the direct research limits, but still, because they have a multiplicity, still enhance the signatures in precision measurements. So let me now turn. Sorry?
4 minutes, sorry, 4 minutes left.
It's okay. I think I have 5, but it's okay.
Okay, but 5 then, fair enough.
Right, or maybe 6. Right, anyway, I mean, it's okay. So if we start from the 10D in the fermionic language, so we start with this basis, then in 10 dimensions, the SUSY generator is given as a combination of this basis vector. So if we break, say, E8 cross E8 to SO16 cross SO16, then this breaking is correlated with the breaking of space-time supersymmetry. So we get the tachyon-free, non-SUSY 10-dimensional string vacuum. And it is tachyon-free because the projection of the tachyons is just by virtue of the existence of this vector in the additive group. Now, the other vacua in 10 dimensions that are tachyonic are obtained by removing S from from the basis, and that will produce tachyonic 10-dimensional vacua. Now, in both cases, we can construct tachyon-free 4-dimensional vacua by choosing appropriate GSO configurations. So this is what we have been pursuing. Now, this is obtained so we can construct model by having another one of these modular maps where the S vector that I had before is modified to an S tilde model. So that just by this modular map. So now we can take any model that we had before and just do this map, and then this would correspond to a compactification of one of the tachyonic 10D vacua, and then we can look into the features or how it sort of compare between what is modified, what is maybe maintained in this map. And together with my students, Victor Matthias and Ben Percival, we have sort of extended the classification by looking at this vacua with S tilde, so using this modular map. So some of our results. So for example, we see that there are no viable S tilde models which have, say, flipped SU5 or Patis-Salam symmetry, because they don't have the heavy Higgs representation that are scalar heavy Higgs representation are required to break the non-abelian GAD group. So only standard model-like configurations cross a U1Z prime are allowed because we can break the Z prime symmetry using states that have exotic charge under the Z prime. The standard model singlets, but have exotic charge under the Z prime. And then we analyzed, say, distribution of the cosmological constant. For example, since I'm running out of time, and the sort of models that have NB equal to NF, so vacuoles that have an equal number of fermion and boson at the massless levels, and we can see that many examples that have an equal number of boson and fermions. So just to finalize, since I'm coming to the end of the 25 minutes, so we can extend this analysis of modular maps to two dimensions. It's particularly interesting in two dimensions because in two dimensions there is a very rich symmetry structure that is studied in what's called the moonshine. Essentially, it's a symmetry structure of 24-dimensional lattices, and we can compactify the two dimensions and then have this. So you have 24 so complex fermions divided by 4. So you can have a basis with a total of 6 such modular maps, and then together with my student in Liverpool, Panos Athanasopoulos, we played with this, and we looked at the classification of the different group configurations, and we produced a representation of the 24-dimensional linear lattices. So one interesting possibility is, for example, to see the spin-off vector duality as emerging from these symmetries of the moonshine, or the 24-dimensional lattices. Right, so I think Brent is telling me that I have reached the end of my time. So with this, I would like to thank you very much again for very nice organization of the conference. I think the talks were very interesting, and so I will leave the conclusions on. Right. So Brent, is that am I on time?
You're right on time. Thank you very much. Thank you, Alon, for your talk. We could take a couple of questions and then maybe leave it to Jim or Fabian to conclude the conference.
So I have to announce the next year.
Yes, absolutely. Please do.
So so let me do that now. Right. So next year the conference will be between the 4th and 8th of July, and it will be in Liverpool. So everybody is invited, hopefully, to come in person to Liverpool. But I think that at this time it's unpredictable. So.
Well, let's hope so. Thanks again, and we're looking forward to that next year, seeing everybody again, hopefully in person. Are there any questions? I'm scanning through the participants list. I see one from Ivano. Go ahead.
Yes. Hi, Alon.
Hi.
Hi. Nice talk. So I was wondering. I mean, we have talked in the past about the potentially problematic back reaction of the SUSY breaking ingredients. But what I believe I haven't asked you yet is how much of these desirable features that you found you expect to survive the SUSY breaking back reaction. It usually is quite dramatic in these kinds of models.
Yeah, no, absolutely. I think that it's at this stage, I would say it's just playing around. But I will, so we discussed the possibility, say, of stabilizing, right, using a different sort of mechanism in non-supersymmetric configurations, or how to cancel the tadpole in a different way. So that's a question that needs to be explored. I mean, you have to put this on curved backgrounds and then look at well, I would say that especially when we will want to extend the analysis of string vacua. We understand string theory only in the static limit. Once we want to extend string theory, proper string theory, to a more dynamical picture, say, of the early universe, we will have to understand how this non-supersymmetric or even tachyonic configuration are incorporated in the picture. So I think that's inevitable. And so, at the moment, I don't know if, so for example, I mean, I discussed one of the examples that we had here. We argued in this paper that in this paper, which was constructed as a supersymmetric model, but we couldn't find flat directions. We couldn't find exact flat directions. So here we analyzed this model just by doing this S tilde map. Now, the implication was that it was supersymmetry will be broken because they couldn't find we couldn't find exact flat directions, so we couldn't find exact, say, F flat directions. So it will be broken at some order in the superpotential. And yet there are no moduli. We argued that all the moduli are projected out. It's a model where you twist very violently the internal space by asymmetric assignment. You break the gauge symmetry to the star model gauge group. So it's a very sort of special configuration, completely not generic. So now. So how much now this is sort of it's a tachyon-free model, but it's a non-supersymmetric. So does this survive this map? I mean, for example, that needs to be investigated. I don't know the answer to that. I mean, but definitely I think it would be interesting. So we discussed the kind of technology that would allow you to explore these questions.
Right. Yeah, it would be interesting to find a bulk description, a space-time gravity description, if available, to these kinds of things.
Yeah, it is available. I mean, it is it's not trivial work, but the technology is available.
Very interesting.
Thanks for that answer.
Thank you.
I'm going to